What happens when a human structure becomes heavy enough to interact with planetary physics? What happens when the Yangtze River is transformed from a fast-moving sediment-rich river into a reservoir of about 39.9 billion cubic meters of water, which is about 1.4 trillion cubic feet, or roughly 9.6 cubic miles, trapped behind the largest gravity dam ever constructed? Can a hydroelectric project really lengthen Earth's day, alter the moment of inertia of the planet, reactivate dormant faults beneath the Wuxia Gorges, and reshape sediment transport all the way to the Yangtze Delta near Shanghai? The Three Gorges Dam is not merely a concrete wall across the Yangtze River. It is a giant geophysical experiment unfolding in real time. Hidden behind the spillways, penstocks, Francis turbines, shiplocks and cofferdams is a far more fascinating story involving crustal deformation, poor water pressure, reservoir-induced seismicity, sediment starvation, hydrostatic loading, slope instability, and Earth's rotational dynamics itself. When engineers completed the impoundment of the Three Gorges Reservoir and raised the water level to 175 meters above sea level, which is about 574 feet, they unknowingly performed an enormous mass redistribution experiment on Earth. Roughly 39.9 billion cubic meters of water, weighing close to 40 trillion kilograms, or about 42 billion tons, or about 88 trillion pounds, were elevated high within the narrow canyon system of the Yangtze River Valley. That mass shift altered Earth's moment of inertia in the same way a spinning figure skater slows down by extending her arms outward. Conservation of angular momentum requires that when mass moves farther from the rotational axis, rotational velocity decreases slightly. Scientists from the Jet Propulsion Laboratory calculated that the Three Gorges Reservoir increased Earth's moment of inertia enough to lengthen the day by approximately 0.06 microseconds. That translates to roughly 2.2 milliseconds over a century. In normal human experience, such a change is completely imperceptible. No clock on Earth would visibly drift because of it. Yet the significance lies in the principle itself. A human-made reservoir had become large enough to create a measurable planetary signal. Earth's rotation, Earth's oblateness, and even the position of the geomagnetic poles responded microscopically to the reservoir load created behind the Three Gorges Dam. The physics behind this phenomenon is remarkably elegant. Earth rotates with angular momentum defined by the equation I multiplied by omega equals constant, where I represents the moment of inertia and omega represents angular velocity. The Three Gorges Reservoir effectively moved an immense amount of water mass outward relative to Earth's spin axis. Because the total angular momentum of the Earth system remains conserved, the increase in moment of inertia forced a tiny reduction in rotational speed. The effect resembles what happened during the Sumatra earthquake in 2004, although in the opposite direction. That megathrust earthquake redistributed tectonic mass closer to Earth's center and shortened the day by several microseconds. The Three Gorges Dam did the reverse by lifting water upward and outward. The result was a slight slowing of Earth's spin and a minute reduction in Earth's equatorial bulge. Yet rotational change is only the beginning of the geological consequences produced by the reservoir. The most immediate effect occurred beneath the surface, where the enormous hydrostatic load began deforming the crust itself. The lithosphere beneath the reservoir is not perfectly rigid. Rock behaves elastically over large scales. When the reservoir filled, the crust beneath the Yangtze Valley bent downward under the colossal weight of the stored water. Satellite geodesy, global positioning system measurements, gravimeter readings, and crustal deformation models confirmed that the Three Gorges Reservoir produced measurable subsidence and uplift patterns around the impounded valley. Researchers modelled the reservoir as a gigantic elongated lode approximately 60 kilometres wide, about 37 miles wide, and 600 kilometres long, about 373 miles long. The crust beneath the water sagged slightly, while adjacent areas experienced subtle uplift responses. Surface gravity measurements also changed because gravity depends directly on local mass distribution. The stored reservoir water altered the regional gravity field enough for sensitive gravimeters and satellite observations to detect it. The Yangtze River Valley essentially became a giant flexural basin. The crust beneath the reservoir compressed downward while the surrounding mountain blocks adjusted to the new stress field. These stress changes then interacted with ancient fault systems already buried beneath the Three Gorges region. This is where the story becomes far more dangerous. Before the Three Gorges Reservoir reached full impoundment, seismic activity in the region remained relatively modest. After water levels rose dramatically between 2003 and 2010, earthquake frequency increased sharply. Studies showed that the region shifted from roughly 2 moderate earthquakes annually before impoundment to approximately 14 measurable earthquakes per year afterward. This phenomenon is known as reservoir-induced seismicity. The mechanism involves poor water pressure and fault lubrication deep within fractured rock layers beneath the reservoir floor. The geology of the Three Gorges region contains numerous pre-existing faults, fractures, bedding plains, crushed rock zones, and permeable sedimentary layers. Under natural conditions, many of these faults existed near mechanical equilibrium, held stable by friction and confining stress. Once the reservoir filled, water began infiltrating downward through fractures and permeable formations. As poor water pressure increased inside fault zones, the effective normal stress holding the fault surfaces together decreased. In simpler terms, the water acted as a lubricant. Faults already close to failure suddenly required far less stress to slip. Researchers investigating a magnitude 5.1 earthquake beneath the reservoir in 2013 found precisely this mechanism at work. Seismometers identified a narrow seismic zone beneath the reservoir aligned with a previously unmapped fault. The fault intersected geological layers directly influenced by reservoir infiltration. The impounded water increased pore pressure within the fault zone until slip occurred. Importantly, the Three Gorges Dam itself remained structurally stable during these events. The concern was not catastrophic dam failure from a single earthquake. The concern involved the gradual activation of geological instability throughout the surrounding region. The reservoir triggered more than earthquakes. It also destabilized entire mountainsides along the Wuxia Gorges and neighbouring sections of the Yangtze Valley. As water levels rose during impoundment, steep slopes that had remained stable for centuries suddenly encountered new hydrogeological conditions. Reservoir water infiltrated into weathered rock, colluvium, gravel deposits, and fractured clay-rich layers along the valley walls. The infiltration increased pore water pressure within the slopes, while simultaneously weakening internal friction between rock layers. At the same time, the reservoir physically eroded the toe support of many slopes. Under natural river conditions, the Yangtze River flowed rapidly through confined channels. After impoundment, wave action, fluctuating reservoir levels, and shoreline saturation altered the mechanical stability of the valley walls. Many slopes entered what geologists call intermittent creep. Rather than collapsing immediately, the hillsides began moving slowly in pulses controlled by rainfall, reservoir level fluctuations, and groundwater saturation cycles. Hundreds of landslides were eventually catalogued throughout the Three Gorges Reservoir area. Some involved relatively small slope failures, while others displaced tens of thousands of cubic meters of earth and rock into the reservoir. One major landslide in 2009 sent between 20,000 and 50,000 cubic meters of material crashing into a flooded gorge section, which is about 26,000 to 65,000 cubic yards. These failures were strongly connected to hydrogeological processes. Water entering permeable layers became trapped above impermeable clay horizons, forming perched groundwater systems inside the slopes. The trapped water acted almost like a hydraulic wedge, increasing internal pressure and weakening the mechanical cohesion of the hillside. The danger of rapid impoundment had already been demonstrated decades earlier by the Yangtze Dam disaster in Italy. There, reservoir loading destabilized a massive mountainside that collapsed catastrophically into the reservoir, generating a deadly mega-tsunami. Engineers understood the risk very clearly during the Three Gorges impoundment process. That is why thousands of monitoring instruments such as piezometers, inclinometers, extensometers, tiltmeters and global positioning system devices were installed throughout the reservoir slopes before water levels rose significantly. These instruments continuously monitored pore pressure, slope displacement, groundwater behavior and crustal motion. The reservoir was therefore filled in carefully controlled phases rather than all at once. The first phase raised water levels from approximately 66 metres to 135 metres, or about 218 feet to 443 feet, in only 15 days. Engineers then paused for several years to study slope stability responses before continuing higher impoundment stages. The second phase increased levels to 156 metres, or about 512 feet. The third phase eventually reached the final operational elevation of 175 metres, or about 574 feet, in October 2010. This staged impoundment allowed the crust and surrounding slopes to adjust gradually to changing hydrostatic loads. Engineers also stabilized vulnerable slopes using rock anchors, retaining systems, drainage galleries, reinforced concrete supports and dewatering systems. The geological transformation extended far beyond earthquakes and landslides. The Three Gorges Reservoir also fundamentally altered the sediment dynamics of the Yangtze River. Before the dam existed, the Yangtze carried enormous quantities of suspended sediment downstream from erosion zones, mountain landslides, tributary systems and riverbank collapse. Estimates suggest the upper Yangtze transported roughly 40 million tons of sediment annually. Once the river entered the slow-moving reservoir behind the dam, water velocity decreased dramatically. Sediment transport depends heavily on flow velocity. When velocity drops, suspended particles begin settling out of the water column. Sand, silt, clay and organic material accumulated on the reservoir floor instead of continuing downstream. Today, the Three Gorges Reservoir traps approximately 70 to 80% of the Yangtze River's suspended sediment load. Downstream conditions now resemble what hydrologists call hungry water conditions. Water released from the dam contains far less sediment than natural river flow, yet it still possesses substantial kinetic energy. Because the water is sediment-starved, it aggressively erodes riverbeds and riverbanks downstream in an attempt to regain equilibrium. This process has already lowered sections of the downstream Yangtze River channel by several metres or several feet. Riverbed incision threatens bridge foundations, destabilizes embankments, alters aquatic ecosystems, and changes groundwater interactions along floodplains. Historically, Yangtze floods carried nutrient-rich silt into the Jianghan Plain and the Yangtze Delta. Those sediments contained phosphorus, nitrogen, organic matter, and fine mineral particles that naturally fertilized agricultural land. Now, much of that sediment remains permanently trapped inside the reservoir. Agricultural regions downstream increasingly depend on synthetic fertilizers because the annual replenishment of fertile flood-borne sediment has declined dramatically. Shanghai itself exists partly because of sediment deposition from the Yangtze River over thousands of years. Reduced sediment delivery to the Yangtze Delta may gradually increase vulnerability to coastal erosion, subsidence, and flooding over long timescales. Engineers attempt to manage sediment accumulation using a store-clear-release, muddy strategy. During summer monsoon floods, when sediment concentration is highest, low-level silt-flushing gates are opened to allow sediment-rich water to pass downstream. During clearer winter flows, water storage increases again. However, this strategy removes only about 30% of incoming sediment. Over decades, reservoir sedimentation remains an unavoidable challenge. Even the concrete structure itself became a geologic and thermodynamic challenge during construction. The Three Gorges Dam required approximately 27 to 28 million cubic meters of concrete, or about 35 to 37 million cubic yards, making it the largest concrete pour in human history. Mass concrete behaves differently from ordinary structural concrete. As cement hydrates, it releases heat through exothermic chemical reactions. In a structure hundreds of feet thick and more than 2 kilometers long, about 1.24 miles long, heat generated inside the concrete becomes trapped. If the interior temperature rises excessively while the exterior cools more rapidly, thermal gradients produce severe internal stresses. The result can be thermal cracking, capable of weakening the structure permanently. To control this process, engineers embedded thousands of kilometers of chilled steel cooling pipes, about 9,500 kilometers, or about 5,900 miles, throughout the dam body before pouring the concrete. Cold Yangtze River water initially circulated through the pipes. Later, refrigerated water from large cooling plants reduced concrete temperatures further. Engineers also cooled aggregates before mixing and even used shaved ice instead of liquid water in some concrete batches. Conveyor systems insulated the concrete mix while transporting it across the construction site, so temperatures remained near 7 degrees Celsius, about 45 degrees Fahrenheit, despite intense summer heat. Artificial fog systems surrounded portions of the dam during construction to reduce solar heating and prevent excessive evaporation from freshly poured concrete surfaces. Even the spillways reflect the geological concerns surrounding erosion and hydraulic energy dissipation. High-velocity water discharge from the spillways could potentially erode soil and rock near the dam foundation. Engineers solved this using specialized concrete spillway chutes that launch water upward into the air before it falls nearly 100 meters, about 328 feet, away as fine droplets and mist. By dispersing the water's kinetic energy through the atmosphere, the spillways protect the foundation from cavitation, scour, and hydraulic erosion. Its reservoir slightly slows Earth's rotation. Its hydrostatic load bends the crust. Its infiltrating water lubricates hidden faults. Its fluctuating shoreline destabilizes mountainsides. Its sediment trapping transforms the geomorphology of the Yangtze River from the Wuxia Gorges to the Yangtze Delta. That is the deeper story hidden beneath the Francis turbines, ship elevators, cofferdams, spillways, and synchronous generators. The largest dam in human history became a planetary-scale geophysical experiment, proving that when humans reshape a river on this scale, the Earth itself quietly responds.